Hi again. In part two of the lecture, we're going to introduce this concept we've mentioned a few times, differential privacy. So differential privacy arose around 2006, and it's a restriction on the class of algorithms we might use to process information that will allow us to provide rigorous guarantees about confidentiality or privacy, even in the presence of um, arbitrary external information available to an attacker. So in particular, this concept will be able to argue that algorithms that satisfy this concept resist reconstruction attacks and a number of other classes of attacks. And then we'll also try to convince ourselves or think about how we might formulate a claim that it protects against a whole class of attacks that constitute things that endanger the privacy of individual information. Okay, it happens to be a burgeoning field of research, so work on differential privacy has brought up interesting connections to research in algorithms, crypto and security, statistics and machine learning, game theory, databases, programming languages, and also more recently, law and policy. And later in the course, we'll touch on a lot of these connections. Okay, so what's the idea of the definition? So we've got some data set which comes from some domain. We'll denote this X. So every record in the data set belongs to the set script X. And there are n records, so we'll note these x1 through xn. And we're not going to try to constrain too much about what the format of the data is. We'll see different differentially private algorithms that handle different kinds of data. But it could, the data could be numbers, it could be like something complicated like a tax form, whatever it is. In any case, we're going to think for now of the data as a fixed quantity, not a random quantity. So our definition will be worst case over data sets. But we'll think about the process that analyzes the data as randomized. So for every data set X, the output of the algorithm, A of X, is a random variable distributed over whatever space that the algorithm produces outputs in. So those could be pie charts, it could be numbers, vectors, whatever it is. And that randomness can come about in a bunch of different ways. We might add noise to the inputs to our outputs. We might add noise to our inputs. We might do various kinds of resampling in the middle. We'll see a number of ways in which randomness can be brought into the picture. Okay. Regardless of how that is, the notion of privacy will be based on the following thought experiment. Okay, so we're going to imagine taking our data set and replacing one person's real record with some totally bogus record. Okay, so we'll start with the real world. We'll call that, the blue picture, and we'll consider this, alternate reality in which x2, person number two's data, say, has been replaced with some totally different record, x2 prime. And the question we'll ask is if the distribution on the outputs of the algorithm will change significantly when we shift from the blue to the green world. So under the blue, in the blue world, there's some distribution on outputs. It's a probability distribution because the algorithm is randomized. And then there's some other probability distribution on outputs in the green world. And the idea is we'll ask that for any possible set of outcomes of this these two random variables, A of x and A of x prime, the probability of that set of outcomes should be about the same. And so, for example, I might be worried about my data being used by in some medical study that causes down the road my health insurance premium to go up. Okay, so the set of outcomes I might worry about are the ones where my health insurance premium increases. And what this tells me is that the probability of that happening is about the same, regardless of whether or not my data are used in the computation. A little more formally, we'll say two data sets are neighbors if they differ in one person's data. Okay, so for now, we're going to imagine that the length of our data sets is the size of the data set is somehow this fixed number n, okay, that's somehow known. And so when we change one person's record, what we're doing is replacing one of the entries of the data set with some other entry, in this case, x2 prime in the picture. Okay? So two data sets, x and x prime, are neighbors if they differ in just like one entry. Okay? In other words, their Hamming distance is 1. And the requirement is that neighboring data sets induce close distributions on outputs. So specifically, we're going to have a parameter epsilon. It's going to be a real number, a positive real number, that tells us how strict our definition is. We'll say an algorithm A is epsilon differentially private if for every pair of neighboring data sets, x and x prime, and for all subsets of outputs, the probability that we get an output in this subset under x and under x prime should be about the same, and they should differ by a small multiplicative factor. Okay, so we're going to, for reasons that'll be clear later, we're going to work on sort of the logarithmic scale. So the factor that controls how close the probabilities can be, we're going to write it as e to the epsilon. And you should think of this as roughly 1 plus epsilon when epsilon is less than 1. Okay. So what we're asking is that for every set of outputs, the probabilities of the output under dataset X and that same set of outputs under dataset X prime be close together. Okay, so the first thing to notice is that this is a condition on the algorithm. We're not asking that the output have some particular format. It doesn't really matter what the output is. We're really asking about the kind of meaning of the process that maps data to outputs. The other thing to notice is that this definition is parameterized by this number epsilon. Okay, so what is this epsilon thing? Well, it's some kind of measure of information leakage. So you can think of it as actually a measure of closeness between two probability distributions. In fact, it's what mathematicians call them. It provides what mathematicians call a metric in the sense that it satisfies the triangle inequality. And we'll see kind of a little later in a few lectures maybe why this particular choice was made, this multiplicative measure is used. But for now, just think of it as some measure of how close the distributions are, and think of it as a small number, but not super small. So think of it maybe as like 1/10 or 1/2, or 1/4 or 1 in 100, but not 1 in like 2 to the 80, not cryptographically small. Okay, so this is our definition, and now we'd like to see, we've already in fact seen an example of an algorithm that satisfies this definition. And that's our first example is randomized response. Okay, so suppose we want to release the proportion of diabetics in our data set. We saw this example in lecture 1, but I'll go back through it just to make sure it's fresh in everybody's head. So each person's input data is a single bit that's either 0 or 1, indicating whether or not they're diabetic. And we're going to run this sort of randomized response algorithm where each individual rolls a fair die. And if their output is 1, 2, 3, or 4, we report their true value. So we set this quantity yi to be xi. And if the output is 5 or 6, we report the opposite of their true value. So we report the negation of xi. So my output is this list of reported values, y1 through yn. And we've seen that, in fact, given these yi's, we can estimate the sum of the true xi's at least when the data set size is large. Okay, we had this exercise that showed us that we could come up with an estimator whose expected error was about square root of n. So the question I'd like you to think about is, why is it that this algorithm satisfies our criterion of differential privacy? And I think it's worthwhile pausing for a second, pausing the video for a second, and actually trying to solve this for yourself to try and understand what, based on the kinds of things we've seen about randomized response, in what capacity it satisfies our definition, for what value of epsilon. So I will keep going. So it turns out that the algorithm satisfies the definition for epsilon equals the natural log of 2, okay, which is less than 1, more than a half. So let's see why that is. So this is the claim we want to prove, namely that randomized response satisfies differential privacy with the epsilon equals the natural log of 2. All right, so what is it we want to prove? We want to prove, the first thing we're going to do is we're going to fix two data sets, x1 through xn, and so this will be our data set x, and x prime which is, let's say, x1 through xi minus 1. So it's the same. It agrees with x everywhere except one position, let's say I. So I is the position in which these two data sets differ. All right. And for starters, we're going to fix some possible output. So that's also just a list of bits. And because we flip coins independently for each person, if we want to write down the probability that our mechanism, let's call it randomized response like that, of x equals y, we can write that as a product of the probability that y1 equals its value given x1 times the probability that y2 equals its value given x2, and so on. Okay, and so for this particular output, we might ask, well, how different can the probabilities be of seeing this specific output under x and x prime? So we could look at the probability that the randomized response on x produces this output over the probability that randomized response on x prime produces this output. Okay, so what values can this ratio take on? Well, let's see. This value, the numerator here is a product of these n probabilities, one for each of the possible input and each of the positions in the input and corresponding positions in the output, divided by by a similar product on the bottom. And these two products are the same in all but one position. Okay, so what's going to happen is if we take this ratio, everything's going to cancel except two of these products. So this, what's going to be left is the probability that yi was produced in the numerator given xi, and in the denominator given xi prime. Okay. And the way we set it up, because given output 0, we produce output 1 with probably 1/3, output 0 with probably 2/3, and vice versa with input 1. The ratio of these two values will always be either equal to 1/2 or to 2. We saw that in lecture 1. Okay, so what we get is that another way of saying that is that the probability that r of x equals y is at most e to the log 2, which is another way of writing 2, times the probability that randomized response applied to x prime equals this y. All right, so there we go. That's our main inequality. Now, this isn't quite the thing we needed to prove. Okay, so as stated, to prove that our algorithm satisfies differential privacy, let's look at, we have to look at some, an event, possibly much more complicated than just a singleton y, not a single output, but some subset of outputs. Okay, so we're going to look at some set of outputs that, so some subset of strings, of binary strings of length n. And now we want to argue that the probability of this whole set, doesn't go up very much, but actually that follows from our equation star here. Okay, so let's just work that out. So the probability that randomized response on X produces an outcome in E is the sum over those strings in E. Those strings in E of the probability that randomized response produced that specific string. And now by star, that's equal to the probability that the sum, that is, over E, it is at most, that is equal to e to the epsilon times the probability that we get this on input x prime. And now if we just stare at this for a second, we realize we can pull the e to the epsilon up front. And this is the same as the probability that on input x prime, we would get an outcome in the set E. Okay, and that concludes, that's exactly what we wanted to prove. Okay, so that's QED. Okay. So notice this proof, it's important that this argument works for any pair x and x prime and any set E. In this case, everything is very symmetric, so it really didn't matter. That's really, like, we didn't have to use any special structure or anything, so that was easy. Okay, so that's an example of something that satisfies a proof that something satisfies differential privacy. And this example actually highlights this sort of useful trick, which is that in general, if we want to prove that something is differentially private, is epsilon differentially private, it suffices to look at we don't have to look at like big complicated events. It suffices to look at one output at a time, look at what happens to the probability of that particular output, And if for every single output, the probability can't jump by a big multiplicative factor, then the same is true for all possible events. Okay, so we can sort of formalize that a little, a little more generally as follows, that here there are really two equivalent versions of the definition. One is the thing we saw before. This was our original definition here. That looked at all subsets of outputs. And that's completely equivalent to a version where we only, instead of looking at subsets of outputs, we look at specific outputs. And we ask that for every particular thing that might come up as an output, the probability that A of x equals y is within e to the epsilon of the probability that A of x prime equals y. Okay, so I won't go through that proof. We sort of did it for the case of randomized response. And we'll see another example of that in the last part of the lecture. Maybe one thing I should mention is that this type of equivalence is true when the outputs are discrete, like in the case of randomized response, the outputs are strings of bits. More generally, when the outputs are like continuous, say real numbers, if we're say doing things like adding Laplace noise, which we'll do in the next section, or Gaussian noise or stuff like that, then it suffices to compare the density functions of the two distributions, again, point by point, at least for now. We'll see later in the course, and maybe in a couple of weeks, we'll see definite versions of differential privacy, variations on the definition where the analysis is more complicated. But for now, we can go point by point, and we'll be okay. All right, so let me just generalize this a little bit. That one way to generalize this is to imagine we can make randomized response work not just for epsilon equals log of 2, but for any value of epsilon. And again, we saw this in lecture 1 in some form. So first of all, the first generalization we can do is to think of each person's record as coming from some more complicated set, script x. And then we'll be sort of, instead of asking for each of the xi's to just be one bit, what we'll do is we'll assume we're interested in counting some property of the x's, which will encode via some function phi. I'm sorry. So the function phi will tell us for each possible record whether it counts as a 0 or it counts as a 1. Okay, so for example, if I'm counting the number of diabetics in the data set, then I will map records that contain not diabetic to 0 and records that contain diabetic to 1. Okay, and so the thing we want to learn is the sum of over the data set of this phi thing. Okay, and so nice way to do that works for any epsilon, that's any positive epsilon, is to, instead of using the 2/3, 1/3 randomization, to use different probabilities. Namely, we can output, given an input that's either an input z that's either 0 or 1, this R operator, what it does is it maps a bit to itself with probability a little bigger than a half, okay? And it maps it to the opposite value with probably a little smaller than a half. And these are the two values we'll choose, and these two values are chosen exactly so that their ratio is, exactly e to the epsilon. Okay, so these are just two numbers that add to 1 and whose ratio is e to the epsilon. Okay. So you can check for yourself that they add to 1. And because their ratio is e to the epsilon, if we consider the algorithm that sets yi to be r of phi xi for each I, and then we return this vector of values, y1 through yn, then in fact we get exactly, this is the randomized response algorithm, and what we get is that this algorithm is epsilon differentially private for whatever value epsilon we chose. Okay, works for any epsilon greater than 0. And just as with the simple 2/3, 1/3, we can come up with a good estimate of the sum we care about based on these, the outcome of this, the output of this algorithm. So also can we do that using the more general e to the epsilon over 1 plus e to the epsilon versus 1 over 1 plus e to the epsilon algorithm. But that's just a little more complicated. Okay, so the idea, we're going to, as before, we're going to set, again, we're going to set yi to be this randomization. So here's our algorithm. And the way we're going to come up with an estimator is as some linear function of the yi's. Okay. And so an exercise that you'll be asked, that we had some time for in lecture 1 and that you're asked to complete on the homework, is to think about what is it that, what linear function will we have to do, will we have to use to estimate these, to estimate the thing we're really interested in, which is the sum of the phi's. Okay, so if you choose A and B in the right way, then what you get is you get an estimator A, which is a linear combination of these yi's. And it always has the right expectation. So for any data set X, in expectation over the random choices made by the algorithm, the estimator will have the correct value. And it won't, its deviation from that value won't be too large. Okay, so it's about square root of n times some number that is, it's bounded above by square root of n times this number that depends on epsilon. That's about square root of n over epsilon when epsilon is sort of less than 1. And as epsilon goes to 0, this becomes a very good approximation. Okay, so what have we got? We have a definition, this differential privacy, and we've got an algorithm that satisfies it, that allows us to estimate a sum of any predicate over the data set. Now, there's a few things that we'd like to do better. First of all, it would be nice to get the to understand whether or not this is the best error we can get. Like maybe there's another algorithm that adds way less noise, that gets us a much more accurate estimate of the thing we're after for the same privacy parameter epsilon. And indeed, there is. The other thing we could hope to do is to be able to like run much more complicated types of calculations than just estimating the frequency of predicates. And again, that's going to take us well into the middle to end of the semester to see some of the major ideas that come up with that. But even in the next part of the lecture, we'll see like one big tool called the Laplace mechanism that will really help us handle much more interesting calculations.